We'll have our look at the calendar. I will point out that in the next few weeks, we got a couple of appearances of Chapter 1. Now, Chapter 1 is the first chapter in our book, and it is the pre-calculus review chapter. And instead of starting there, you can see that we've got sprinkled in throughout here some appearances of Chapter 1. And so in the next few weeks, we're just going to do pre-calc on 3 different days. And these days are intentionally chosen to be right ahead of the calculus material that they go along with. So today, we're going to review exponential functions, no calculus. Next class, we're going to take derivatives of exponential functions. So that's why we're reviewing exponentials today. After that, we're going to spend a day reviewing trig functions, no calculus. And then the class after that, we'll do derivatives of trig functions. And then likewise with inverse and log functions, that's a pre-calc review. And then we will do derivatives of inverse functions and derivatives of log functions, okay? So they're just sort of like sprinkled in here just in time for us to do calculus stuff. Hopefully we're working on steel drum and pipeline. We've got some take-home quizzes coming up. You don't need to worry about those for right now. Okay, so let's jump in here on page 19. Today we review exponential functions so that we can find and use derivative formulas for them next class. Number 1, suppose an air freshener starts with 30 grams, that's 30 grams of the chemical inside of the air freshener, and then it evaporates. We're going to write a formula for the quantity Q in grams of air freshener remaining T days after the start if the air freshener decreases in 2 different ways. So this chemical is evaporating in 2 ways. One way, we're going to assume it evaporates 2 grams per day. The other way, we're going to assume it evaporates 12% per day. So let's write a formula. Q equals, okay, so in this case, we start with 30 grams. So I feel like that's a good way to start our equation. And if we lose 2 grams every day, let's say subtract 2 T or X, whatever the variable is for the number of days, right? What word describes that kind of function? That is a linear function, right? Changes 2 every single day. That -2 is our slope. However, if we're changing 12% each day, the formula looks fundamentally different. We are still starting with 30. That's a good thing to write down. Okay, if you lose 12% per day, how much remains? What percentage remains every day compared to the previous day? 88%, and we will write that as a decimal. And the way that we account for the fact that we want 88% of what we had the previous day is not to multiply by t, but to do what? Is to raise it to the t. That formula right there, like if you just imagine t is 3 days, that formula right there is going to be 0.88 times 0.88 times 0.888, 3 copies. And that means you take 88% of 88% of 88% of the 30 that you started with. Okay, so that's why exponential is the right thing to do for a constant percentage decrease. Okay, exponential functions can be written in the form p of t equals p sub 0 times a to the t, that's one example, or p sub 0 times e to the kt. How much is p sub 0 in our formula here? Is 30. How much is a in our formula? Is the 0.88. And so I'll remind you that another version of this that you might have seen in your pre-calc class was 1 plus r to the t. And in our case, r is not quite 12%. What is r? P of t equals 30, 1 to the t. How much is r? Is negative 12%, right? 1 minus 0.12. That's the formula. And 1 minus 0.12, of course, is the 0.88. And we figured it out without using the formula, but just want to connect it to something you've seen. Number 3 says, oh, okay, and then the e to the kt, that's just another way to write the formula. It would change the way that it looks, but if you graphed it, it would look exactly the same. E is around 2.7. You've seen that number before. And there's a keyword that tells you to use the second formula, and that's the word continuous. If you see it's continuous growth of 12%, continuous decay of 12%, that's your clue that we're doing the E version of things. Okay, so number 3 says, let's convert our answer from 1b into the form p sub 0 e to the kt, and then we'll write down the continuous decay rate. All right, so we're going to start by copying that thing that we had, 30.88 to the t. And what we really want is for that thing to look like p sub 0 e to the kt. So we are going to change the way it looks. We're going to force it to be in this e to the something. form. Okay, so then we're just gonna like separate our pieces, right? Like clearly 30 is playing the role of the P0. That part's easy. So the harder part is that all of this is supposed to be the same as all of that. So we're just like separating, you know, kind of the obvious pieces. So P sub 0 is for sure 30. And then the other equation is the harder one. 0.88 to the T is supposed to match up with E to the K T. All right, now these T's are roughly in the same spot. And so with justification, we should be able to like cross them both off, like ignore them because they're basically the same. So the justification is to raise both sides to the right power. Do we know what that power is? What can I raise this side by to get rid of that T? Negative T is not going to do it. It's a good guess though. 1 over T is the winner because we know when the powers look like that, we multiply them. And so 1 over T is the thing that's going to turn that power to a 1. And whatever you do on one side, obviously you got to do to the other side. So we raise both sides to the 1 over T, and then the T's just disappear. And so we get a simpler equation. 0.88 equals E to the K, because the T's cancel on the right-hand side and just multiply. Yeah. And so the final step here is to find K. Remember E, I mean, it's a letter, but it's not a variable. It's not like a K. E is around 2.7. Yeah, and so to solve an equation where the variable's in the exponent, you guys know you use logs. Now we're going to talk about logs more formally in a couple of classes, but right now we'll just take the ln of both sides. So I'll copy that same equation again, but with a little bit of space in front. And then we take the natural log of both sides. And the point of doing that is that what do you get when you simplify the right-hand side? You just get K, because ln of E to the K, ln and E are inverses of each other. They cancel. And so that's just K equals, and then ln of 0.88 is it. And we can go ahead and get a decimal up here. What is it? What, 2? 7. That sounds good. And so that means that we can rewrite our Q formula, 30 e to the negative 0.127, oops, 127 d. Yeah, Daniel. You could absolutely leave it as ln of 0.888. Yeah, that's more accurate than our negative 0.127. Yeah. Okay, but the idea is that if you were to graph this function here on your calculator and you were to graph the original 0.88 to the t function on your calculator, they would land right on top of each other. Although, as Daniel points out, it wouldn't be perfect because we've got a little bit of rounding in our 0.127 version. But that's the idea. And so that negative 0.127 is called the continuous decay rate. Continuous decay rate is negative 12.7%. It's just the value of K. That's what we call the continuous growth rate or continuous decay rate. And it's not too far from the 12%, right? Like we were given 12%. So that 12% per day is the equivalent of 12.7% continuously every moment of the day, losing 12.7% of the chemical that's in the air freshener. Questions on that? Okay, so the activity starts on the next page. Largely it is pre-calculus stuff, although we will have you drawing some tangent lines and making some guesses as to where we're going with derivatives next class.